This module introduces the transmission and bearing sections of positive displacement motors. Building on power section principles, we now focus on how torque is transferred, how bends are adjusted, and how bearings sustain loads. This is the second submodule of 3. At the end of this module, you will achieve a set of key learning objectives. You will be able to explain the role of the transmission assembly in transmitting torque and thrust while absorbing rotor eccentricity. You will understand how adjustable bent housings provide flexibility in directional drilling with common bend specifications enabling short radius or conventional applications. We will also cover the process of adjusting a bent housing from braking connections to setting and torquing the new bend angle. In addition, you will gain insights into bearing section designs, contrasting mud-lubricated and oil-lubricated systems, and evaluating their features, costs, and suitability for different environments. We will examine radial bearings and axial bearings, including how hydraulic thrust interacts with weight on bit to determine actual bearing load. You will also learn how to interpret motor performance in terms of RPM, torque, and pressure, and how to read power curves for operational decision-making. Finally, we will link motor design and performance to bit selection, understanding how different bit profiles and aggressiveness affect tool face control, weight transfer, and vibration management. These objectives will prepare you to apply PDM principles effectively in planning and execution. The transmission assembly of a PDM serves as the mechanical link between the motor's power section and the bit. Its primary function is to transfer torque and thrust generated by the rotor and stator into the drill bit while absorbing the eccentric movement caused by rotor nutation. This is achieved through universal joints, often called U-joints, which allow the angular misalignment to be smoothed out. By converting eccentric motion into consistent rotary motion, the transmission ensures efficient energy transfer and protects the lower assembly components from damage. Modern U-joint systems are built from high-strength alloys and feature optimized designs that maximize fatigue life, even under high torque conditions. Proper lubrication and alignment are critical to prevent premature wear, as U-joints are subject to intense stresses from cyclic loading. Failures in the transmission can lead to catastrophic bit performance issues or unexpected downtime, making this section a focal point for maintenance and inspection. The adjustable bent housing is an essential directional component built into a steerable PDM assembly. Its purpose is to introduce a slight angular deviation between the motor housing and the bit, creating a controlled side force that allows the well trajectory to be altered. Typical specifications are 0 degrees to 2 degrees, 0 degrees to 3 degrees, and 0 degrees to 4 degrees, providing options for tangent build or short radius drilling applications. The transmission shaft runs through the housing, and the bend angle can be set depending on the directional objectives. The adjustable bent housing allows drillers to switch between rotary and sliding modes seamlessly. With the housing aligned straight, the motor drills a smooth path, while introducing a bend allows tool face orientation to guide the wellbore. Choosing the right bend angle depends on the desired build rate, formation type, and bottom hole assembly design. Too aggressive, a bend may increase the risk of high doglegs and tortuosity, while too little may limit the ability to achieve directional targets. The adjustable bent housing, therefore, offers flexibility and control, but must be carefully selected and managed to balance steerability with motor life. The bend is normally pre-agreed at the BHA design stage and set up in the maintenance facility, but it is possible to change it on the rig floor if required. A large hole requires a greater bend to deliver a dogleg compared to smaller hole sections. Also, the higher the bend angle, the lower the maximum RPM that can be rotated from surface, which will impact hole cleaning. The reduction in RPM is due to the additional stress caused by the bend. Adjusting the bend angle on an adjustable bent housing is a straightforward but critical procedure that must be carried out with precision. The first step is to break the connection located below the lock housing, which secures the adjustable section. Once the connection is freed, the housing can be rotated to align with the required bend angle, which is usually marked on the tool in discrete increments such as 0.5 degrees or 1 degree. After the desired angle is set, the connection is tightened and torqued to specification, ensuring the housing is locked in place and capable of withstanding operational stresses. Proper adjustment directly influences the build rate achievable during drilling. For instance, a higher bend angle is used when a sharp curve or directional correction is required, while lower angles provide smoother changes in trajectory. The bearing section is responsible for carrying both radial and axial loads while transmitting torque to the drill bit. This section typically includes radial bearings to stabilize the rotating shaft and axial bearings to handle the weight on bit and hydraulic thrust. Mud lubricated and oil lubricated systems are two main designs. Mud lubricated bearings use drilling fluid as both a coolant and lubricant, making them common and cost-effective, though more prone to erosion. Oil lubricated bearings, less frequently used, enclose lubrication oil in a sealed chamber, providing superior protection in harsh environments, but at higher cost and maintenance complexity. The bearing section also includes a single-piece forged drive shaft, which minimizes weak points and improves durability. Proper operation balances load distribution between radial and axial systems, maximizing tool life. Drillers must carefully monitor pressure drops, torque, and weight on bit to prevent overload and ensure that bearings operate within their design envelope. Here we compare mud lubricated and oil lubricated bearing systems in terms of features and applications. Mud lubricated systems dominate field use because they are simple, inexpensive, and compatible with standard drilling practices. In this design, drilling fluid flows through the bearings, cooling and lubricating the surfaces while also removing debris. However, these bearings are more vulnerable to erosion, particularly in high solids mud, and require careful monitoring of hydraulic conditions. Oil lubricated bearings, on the other hand, use a sealed oil chamber to isolate the bearing surfaces from drilling fluid. This system reduces wear and erosion dramatically, making it suitable for highly abrasive formations or sensitive drilling fluids. The trade-off is cost. Oil lubricated designs are more expensive to manufacture and maintain, and they often require special servicing. While they are not commonly used, their reliability in extreme environments justifies their application in high-value wells where downtime is costly. Radial bearings are designed to stabilize the motor shaft and resist side loads encountered during drilling. They are lubricated by drilling fluid which flows through small clearances, cooling the bearing surfaces and limiting friction. Proper flow regulation is essential, since inadequate lubrication can quickly lead to overheating and failure. The amount of fluid directed through radial bearings is influenced by the bit nozzle pressure drop and the clearance between bearing surfaces. Manufacturers generally recommend a minimum bit pressure drop of 250 psi for standard designs and 100 psi for low pressure drop designs to ensure sufficient flow. By maintaining these pressure thresholds, the bearings receive enough cooling while allowing adequate hydraulic energy to reach the bit. Radial bearings work in conjunction with axial bearings to manage total loads. When radial stabilization is compromised, vibration, shaft misalignment, and accelerated wear in other motor components can occur. Axial bearings carry the vertical loads imposed on the motor. These loads come from two sources: weight on bit, which pushes upward through the motor, and hydraulic downthrust created by fluid flow. To handle these forces, axial bearings are built with multiple ball races that distribute load across larger surface areas, reducing stress concentrations. During drilling, when weight on bit is applied, the axial bearings must resist upward thrust. When circulating off bottom, back reaming, or operating with insufficient weight on bit, hydraulic thrust dominates and applies downward forces. The actual bearing load is calculated as weight on bit minus hydraulic thrust, meaning engineers must balance these opposing forces to optimize performance. Excess weight on bit can overload bearings, while insufficient weight on bit increases hydraulic thrust effects, both scenarios reducing bearing life. Mud lubricated axial bearings rely on drilling fluid for cooling and lubrication, which underscores the importance of managing solids content and mud chemistry. Failures in axial bearings manifest as loss of torque transfer, erratic bit behavior, or complete motor failure. The bearing condition can be monitored when the motor is at surface by setting down weight on the rig floor and measuring the play on the bit box to the motor. 2 mm is good, 5 to 6 mm is showing wear, and the motor should be changed. Greater than 10 mm indicates possible bearing failure. This slide emphasizes the importance of balancing axial thrust for reliable motor performance. When fluid flows through the motor, it creates a downward hydraulic thrust, while weight on bit applies an upward thrust. If these are not balanced, bearings will be overloaded in one direction, causing premature wear. The equation used is actual bearing load equals weight on bit minus hydraulic thrust. This means that effective drilling requires engineers to optimize bit hydraulics so that thrust forces are offset as much as possible. The choice of bit nozzle configuration directly impacts hydraulic thrust, since pressure drop across the bit influences how much fluid is directed through the motor and bearing system. For example, higher bit pressure drops increase cooling and lubrication, but also change thrust balance. Drillers must therefore consider nozzle selection in relation to both hole cleaning and bearing longevity. Maintaining balanced thrust improves motor run times and reduces failures, particularly in long lateral sections where motors experience sustained loading. Looking at the chart on the right for an A700 GT motor, the balance between thrust load and applied weight on bit must remain within the dotted lines with a hard limit shown horizontally. The performance of a PDM is defined by relationships between RPM, torque, and pressure. Several rules govern these dynamics. Increasing the number of lobes in the rotor-stator assembly increases torque but decreases rotational speed. More stages in the power section increase torque and allow higher pressure handling. Tighter rotor-stator fits provide greater torque but also increase slip, resulting in higher differential pressure and reduced elastomer life. Excess pressure accelerates elastomer wear, shortening motor life. Operators must therefore optimize these parameters for drilling conditions. For example, when drilling hard formations, high torque is desirable, so motors with more lobes and stages may be chosen. In softer formations, higher RPM is more beneficial, so motors with fewer lobes can improve penetration rates. Managing pressure is equally critical. Overloading the motor with excessive differential pressure can lead to stalls or stator failure. Power curves are probably one of the most misread curves and also the simplest when you understand. The top graph deals with the bit RPM and torque generated by the power section. The bottom graph deals with the horsepower generated by the power section. In the top graph, 3 RPM curves are presented: minimum, medium, and maximum flow range. At a differential pressure of 0, the RPM values for a specific flow rate are the off-bottom or runaway speeds. RPM is proportional to flow at no load or off-bottom. As the weight on bit increases, the resistive torque on the motor increases. As a result, the differential pressure across the motor increases and the rotor slows down. This RPM decrease is due to leakage. The leakage is the flow of mud through the rubber to steel seal created between the rotor and stator. As pressure across this seal increases with increasing torque, more fluid leaks past the seal, decreasing the RPM for the same flow rate. The torque line on the RPM plot indicates the amount of torque that the power section can deliver as the differential pressure across it increases. Torque is linear with respect to differential pressure. On the bottom graph, the horsepower is related to the output torque and RPM of the motor. Reading the graphs, take an example of a differential pressure of 300 psi. In this example, we are also pumping at 600 gallons per minute. What is the RPM, what is the torque, and what is the horsepower? On the top graph, draw a line vertically from your differential pressure reading to meet the red curve, which represents a flow rate of 600 gallons per minute. Then draw a horizontal line to the left-hand scale. The RPM is approximately 150 RPM. To measure the torque, we draw a line up from the differential pressure, and where it intersects the torque line, draw a horizontal line to the right scale, which reads 2,900 foot-pounds. To calculate the horsepower output, go to the bottom graph. Draw a line vertically from your differential pressure reading to meet your interpolated flow rate curve. In this case, it's the red curve, and draw a horizontal line to the left-hand scale. This reads approximately 92 horsepower. The differential pressure is the difference between the pressure observed when the BHA is on bottom and when it is off bottom. These graphs are different for each of the motor types. Usually, they are given in a motor handbook for field use. Choosing the right bit is essential to achieving directional objectives while maintaining motor integrity. For roller cone bits, tool face stability is often easier to maintain, since changes in weight on bit cause only minor variations in torque. This makes them suitable when tool face control is a challenge. Polycrystalline diamond compact (PDC) bits, however, offer superior durability and rate of penetration, but are highly sensitive to weight on bit changes. Small increases in weight can lead to significant increases in torque, complicating tool face control and increasing the likelihood of stalling. Matching bit aggressiveness to motor torque capacity is critical. Aggressive PDCs may outperform in soft formations, but must be carefully paired with motors designed for high torque delivery. Bit profiles also matter. Long gauge bits are better for tangent sections, providing smoother drilling and reduced doglegs. Conversely, flat bottom or shorter profile bits enhance build capability, enabling higher dogleg severity where directional changes are needed. Engineers must also consider hydraulic requirements. Bit nozzle configurations influence fluid flow, affecting both hole cleaning and axial bearing thrust. The graph shows how weight on bit interacts with bit aggressiveness to influence motor performance. The aggressiveness of a bit face defines how torque responds to applied weight. Roller cone bits are less sensitive. Large changes in weight on bit produce only slight increases in torque. This makes them easier to control in fluctuating weight conditions and less prone to stalling. PDC bits, however, are much more sensitive. Even small variations in weight on bit can double torque demand, complicating tool face control and leading to stalls if torque exceeds motor capacity. This difference highlights why tool face stability is more difficult to maintain with PDC bits, particularly in formations with variable hardness or where weight on bit fluctuations are common. Now that we've covered the content, let's revisit the module objectives. You should now be able to explain the role of the transmission assembly in transferring torque and thrust while absorbing eccentric motion. You understand the purpose and use of adjustable bent housings, as well as the process for setting bend angles. We explored bearing section designs, comparing mud-lubricated and oil-lubricated systems, and highlighted how radial and axial bearings distribute loads. We examined thrust balancing and learned how weight on bit and hydraulic thrust interact to determine actual bearing load. We also reviewed key operational principles, including the relationships between RPM, torque, and pressure, and how these are influenced by motor design. Power curves were introduced as essential tools for predicting performance and avoiding stalls. Finally, we studied bit selection, noting the differences between roller cones and PDCs and how bit aggressiveness and weight on bit affect tool face control and motor performance. Together, these objectives equip you with a comprehensive understanding of how PDM components and design choices impact drilling performance. Thank you for your attention throughout this module. Please proceed to the quiz.